it's a pleasure to have Steve Rayan. He's going to talk about quantum matter and algebraic geometry and number theory. Thanks very much.
Thanks so much, James, for the introduction. Are we recording or?
Yes, we are. Yeah.
Okay, perfect. Yeah, well, thanks, James, for the warm introduction. I just want to thank Yang for the invitation to speak here, and all the organizers for the excellent work they've done putting together this fantastic conference, and Ed as well for being such a technologically adept a host for everything. I really do think that this has been just an absolutely terrific couple of weeks, and really one of the best online conferences I've been to, in the last 17 months or however it's been. I think that this event has managed to sort of capture the grandeur and the energy of in-person interaction, but in the virtual format. And at the same time, taking advantage of the virtual format to make this really truly global. I really enjoyed that. So just kudos to everyone involved. And my talk today, it's a little bit different from the last two we heard. I mean, for connectivity, and in retrospect, I could have given a talk that would have been a good follow-up for the first one we heard this afternoon, morning for me, but I think afternoon for a lot of other people. But I think I'll say something just a little bit different. A lot of what we've been hearing in this conference has had to do with geometry and its interactions with high energy physics. And this is going to, sort of go to the other end of the spectrum, and we're going to talk a little bit about condensed matter, in fact, quantum matter. So really at the sort of other end of the energy scale. But this is an area which is starting to have really interesting interactions with geometry, and also, as you can see from my title, a bit of number theory as well. And I won't assume that anyone, has had any exposure to, say, condensed matter. I'm going to be very informal in this talk, and I'm going to try and tell the story, mostly through pictures, if I can. There won't be a lot of symbolism going on here, and I hope that that's amenable to everyone. If you're whether you're versed in this or not, I hope that the way it's presented will be enjoyable. Okay, just want to make sure everyone can hear me. Yeah, we're still broadcasting.
Yeah, we can hear you.
Okay, perfect, beautiful, thanks. Okay, and then maybe just because of the global nature of this, just to place where I am. So I'm in Saskatoon, Saskatchewan, in Canada, where that red dot is. It's sort of like, it's Canadian prairies. It's sort of the Canadian Midwest, if you like. So just thought I'd, just make sure we were all on the same page where I am. Also acknowledge that this is what we call Treaty 6 territory in Canada, and the homeland of the Métis. Interested in Canadian history and what's happening with what we call reconciliation in Canada, that's something that you can feel free to educate yourself about if you're so interested. Okay, so here's a still from the Nobel Prize in Physics proceedings, if you like, in fall of 2016. So that fall, the Nobel Prize in Physics was announced for what are called topological materials, okay, both their theoretical prediction and their experimental confirmation. So here is a member of the sort of the prize committee, the learned prize committee, explaining topology to the audience by tearing apart pastry. So I guess this has a good connection with Dan's video from the prior talk. But this got me thinking then, what exactly are, when you hear, as a mathematician, a geometer and topologist, hear topology in the title of a Nobel Prize, I really want to know what's going on. So this was for the moment when I started wondering what this was all about. And by the way, if you're looking very closely on the slides, you can see that the Nobel Prize Committee is not perfect. Okay, just caught that right there. Okay. these topological materials are very important. Here's a kind of popular article from Nature from 2019, that world, just before the pandemic, talking about strange topological materials popping up everywhere. And, they're very, very useful for applications. And probably the big ticket item is quantum computing, but other applications as well, quantum sensing. So these are very important things, and people are trying to make them, people are trying to better understand them. I think at the heart of all of this, my coming into this as a mathematician, I wanted to really know almost what a mathematical definition of these are. And so that's really what I sought for myself. So I think the beginning of the story is to talk about periodic media. So one might want to try to understand waves propagating in a periodic medium consisting of many repeating cells. And there are certain situations in which the behavior of waves can be determined by their behavior in a particular cell. It's called the fundamental cell. So this is really a mathematical theorem due to Felix Bloch, introduced in 1928, to describe the quantum mechanical motion of electrons in crystalline solids, so conductivity in crystalline solids. But actually, his theorem goes beyond this to describe the behavior of any type of wave in any periodic medium. But the application to electronic motion in crystalline solids anticipates a hallmark of condensed matter physics, which is the band theory of electrical conduction, as well as various phenomena that we refer to as Hall phenomena, including the quantum Hall phenomenon. So to tell you what a topological material is, I'm going to start from a mathematical point of view, and I'm going to try and build a model here. So what I want to do is consider a two-dimensional material, which I'm going to model as just the real plane. Okay, so you can think about this in reality as some very, very thin film, okay? And that's going to be my material. And I want to model it as a maybe being highly crystalline. And so that, in mathematical terms, is that I'm going to tile the plane with a lattice, let's say a parallelogram lattice. And this is really my 2D crystal, okay? But it's just a mathematical object. Okay? And I'll call this lattice lambda. And now, to bring in the physics, I want to think about electrons moving on this lattice. And that's, of course, controlled by the Schrödinger equation. Okay, so I have a Hamiltonian here, and I have energy levels, and these are my wave functions, as we know and love. And so this Hamiltonian, has a Laplace. So it's got the Euclidean Laplacian here, and then it has a potential. And I'm going to assume, I want the motion of the electrons to reflect the crystalline nature of this lattice somehow. So I need to build that into the equation. I'm going to build that into H. In fact, I'm going to build that into the potential. I'm going to ask that the potential is periodic with respect to this tiling. So the potential doesn't know whether it's in this cell or that cell. Corresponding values of the potential are exactly the same. So this is my ansatz, if you like. And what happens is there's a basis of wave functions for the solutions to this equation that are quasi-periodic with respect to the lattice under the right periodic boundary conditions. So if I impose again the right kind of boundary conditions, then and typically this lattice would be a square lattice, or in 3 dimensions a cubical lattice. Those boundary conditions will determine the basis wave functions there. And solutions in other cells will be given by a fundamental solution, but modified by some phase factor, some unitary factor out in front. Okay? So this unitary factor has a vector k in here, which depends on the position. And this is what we refer to as the crystal momentum. And these are defined only up to translation in this lattice. So what we do is, what we're really keeping track of to construct general solutions are these momenta, okay? And these are in 2D, of course, given just by points in a torus, okay? Because they really only depend on which cell you're in. And of course, the original position space can also be reduced to a torus. So everything here, the point is that everything here can be reduced to a torus, R2 mod this lattice. Familiar picture to all. Okay, so this is what we've done. But I guess, you know, at some point this was novel in condensed matter, is really the sort of upshot here. So what we have now is a story involving two tori. We have the position space where the electrons are propagating. We have the momentum space where these phase factors in Bloch's theorem are living, and there's a duality between these tori. Okay. So this momentum torus is often referred to in condensed matter as the Brion zone. And you can think about this duality as a Fourier transformation just between position and momentum coordinates. Okay, so working completely in momentum coordinates, I can plot the energy levels coming from my solutions to Schrodinger's equation. So for a particular momentum k, I'll have some discrete sequence of eigenvalues. Oh, my ground state E0 is missing from my notation here. Well, we'll just reindex E1 as my ground state. So just my convention is usually to use E0, but that's fine. The point is, though, that as I vary the momentum coordinate k, I'm also varying these energy levels, and I get a picture that looks sort of like this. So think of this as just a particular direction in this torus. So here's some direction I've picked out. And I get a picture that looks like this or like this. I mean, they're really the same, let's say topologically, except for this this dashed line mu that you see in the two pictures. That's really the difference. Here, you have energies that are sort of on either side of mu, and here mu is intersecting these two energy levels. And I should say that these are groupings of energy levels. These are the filled and the unfilled bands, or the so-called valence and sort of conductive bands. These are sort of the filled states, and these are the unfilled states, and conduction happens when you move between them. And this dashed line here is the Fermi level, or the electrochemical potential. And if the filled bands and the unfilled bands are sort of completely on either side of this, then we're saying that it's very, very difficult for electrons to make the leap from one side to the other, whereas here it's much easier to do so. And this is really, in some sense, the fundamental difference between an insulator and a metal. And these pictures, this is the so-called these pictures are what we call band structures, and this is really, in a cartoon, the band theory of conducting solids or insulating solids, if you like, as well. They're just two different configurations of the same data, if you like. The point is this structure here is really living over this torus here, and this is really just a cross-section of that picture. So this is really where the topology starts to come in. So as long as there is a gap around the Fermi level between the filled bands and the empty bands for all k, the material will be an insulator. And the existence of this gap, if you like, is a topological property. It doesn't really matter what the exact picture looks like, just how it relates, how these bands relate to mu. And this is exactly why topological conductivity is so robust. Okay? We're saying that there can be all kinds of deformations happening in this quantum energy surface, as long as the relationship between these sheets to mu stays the same. Then nothing is really changing about the sort of large-scale conductivity properties of this material. So just as a sort of recap here of what we've been developing, so we went from the symmetry of a lattice to Bloch waves electronic band theory in a kind of natural way, and this gives rise to topological insulators and semi-metals. And I put this cautionary asterisk here because this is all under the right conditions. Typically one needs to have the material supercooled, very, very low temperatures, approaching absolute zero. And then at times, but not always, which is one of the more sort of beautiful developments in this theory, but oftentimes you need a very strong transverse magnetic field, but that's sort of no longer as a stringent requirement for this kind of behavior. But the conditions under which this kind of behavior manifests maybe as a limitation on the ultimate usefulness of these materials. But again, if you follow any developments with quantum computing, that qubits are supercooled anyway. So it's not introducing a new constraint in that kind of technology. Now, just maybe putting more of a lens on conductivity, there's finer information possible than just say insulator versus metal. So again, certain materials at ultra low temperatures and again, say in intense transverse magnetic fields exhibit a curious property. Their conductivity profile is a step function. It's a very sort of famous phenomenon here. So this is sort of a Hall profile. This is part of say the quantum Hall effect. Okay, so for as we vary the magnetic field, the resistance, the Hall resistance, doesn't vary in a sort of the kind of nice way that you would expect, but more with these steps or plateaus. And these steps actually occur at particular values. So h is Planck's constant, E is fundamental charge, and you have these integers k here in the denominator. So you can see that these aren't exactly at equally spaced integer values. The sort of integer here is actually occurring in the denominator here. But regardless, we said that the conductivity is quantized, and then thinking as mathematicians, and this I think a really natural question to ask, but it's certainly the kind of question a mathematician would ask is, do these numbers k, are they counting something? Is there some combinatorial meaning here? And the answer it's sort of conjectured as early as 1982 by Thules and others. And Thules, by the way, is one of the late David Thules is one of the Nobel Prize winners from that 2016 Nobel Prize. And the conjecture is that these quantum Hall numbers are counting the genus of the valence conduction energy surface. So here's a picture produced by a computer, not in my work. But here's a sort of computer-generated picture. There's more three-dimensional of what's happening between valence and conduction bands. And the point is that you have these this discrete countable set of energies, but the grouping of them into these two broad bands means you can really think about this as some kind of double branched cover. And maybe as I say that, you can see the algebraic geometry starting to come in. But it's really a double ramified cover of your Jacobian. And that's a word that I wanted to say for later, but you could probably see that coming as well. But I'll save it for a bit. But a double branched cover of that momentum torus. So if I think about this as my double cover, and I've got my sort of branch points here, these sort of degenerate points. The idea is if I pull away from this globally and view it as a global say compact object over that momentum curve, then it's going to be some let's say Riemann surface, some algebraic curve. Maybe I'll just say Riemann surface. Go to the extent to which this is sort of algebraic or not. Or at least at the very least, it is a topological surface, and it has some genus. And that's the idea of what is really being counted here by the quantum Hall numbers. Here is actually, some, again, another sort of cute cartoon. This was produced for, by Royal Swedish Academy of Sciences, again, for the literature that came out with the Nobel Prize. But you can see electrical conductivity is somehow, proportional to genus of this valence conductivity surface that we're discussing. But I think, as I've been saying these things, I think we're getting a sense that the theory really is not just topological in nature. I do think that, somehow talking about this as a topological theory doesn't, do tremendous justice to what's going on here. And certainly, there are elements of this that are very topological, and of course, understanding. Again, an important invariant here is this ramification locus, this ramification divisor that you see in this picture. That's not how, I should say that's not how this is phrased typically in any of the kind of condensed matter or quantum matter literature. I mean, this would be phrased in terms of course, the first Chern class of this surface and the so-called Berry curvature. This is the language in which you typically see these developments about topological materials. But the point is that one can reinterpret a lot of this in increasingly algebrogeometric or complex algebraic geometric language. And there is some value to that, because then it starts to suggest various kinds of generalizations to the theory. And I should say, I just want to emphasize again, I showed that sort of nature snippet at the very beginning, but topological materials are very, very real, in both 2D thin films and 3D materials as well. There, as early as 2007, 2008, people were just discovering experimentally various kinds of 2D and 3D insulating states. There's cadmium telluride, bismuth antimony, or some of the first ones, mercury telluride, but there's hundreds of known topological materials now, and this has been a real partnership between the physics and, say, algebraic topology. I suggested some topological invariants that are in play here, but there's a very robust sort of dictionary, or if you like, kind of almost crystallographic table of topological materials associated to various topological invariants. So there's this work, this kind of periodic table of Kitaev, but I think in a much broader way, there's been a lot of work in the last few years by people like Dan Freed, Mike Hopkins, Theo Johnson-Freud, topological phases, but really taking the topological sort of understanding, classification of these materials and arbitrary dimension, very, very far, and that's really, really interesting work. And what I'm going to describe here is really a different approach to all of this, which is much more geometric in nature and suggests new forms of quantum matter, which aren't, which are clearly a generalization of what we've been talking about, but departs in certain fundamental features. Okay, so we were here, and I was starting to say that the theory is not just topological, and I want to emphasize first and foremost that when we were dealing with Schrodinger's equation, in this particular unit cell geometry, for instance, a square unit lattice lambda, whatever that lambda that we picked was, that means that this is not just a torus, but this is some elliptic curve. This is a complex algebraic object. This picks out a particular complex structure on our quotient curve, and then so too is the momentum space. It just it picks up a complex structure naturally. And so what we're really talking about here is the position space is an elliptic curve, let's call it E, and then the momentum space, the Brion zone, is the Jacobian variety of E, the Jacobian group of E. And that duality between them is really the Abel-Jacobi map, after some choice of base point, of course. But the point is that really this duality is a standard, well-loved map in sort of complex algebraic geometry. And here we start to see where the points of algebrogeometric generalization come into play. So a basic question that you can stand back from this and ask, and just as a mathematician does, can I replace, let's say, this position curve, that we started with? Again, here when I'm hovering over this curve, I'm really talking about I had R2 and I had electrons that were moving in a way that honors a particular lattice. Can I replace this genus 1 position geometry with genus 2 or some arbitrary genus? Just as a kind of motivating question. Well, that means we're really talking about a kind of higher genus band theory, and we're asking. We don't want to remove ourselves completely from the physics. What we're asking ourselves, is can we engineer a higher genus position space? If so, what is the corresponding Brion zone? What is the corresponding crystal momentum? Is there a band theory of such solids here? And then maybe, just qualitatively, are we seeing more geometry, seeing geometric invariance, coming into play, and maybe less of a focus on topology? Well, in order to produce a genus G position space, well, we're going to have to tile our 2D film differently. It's going to have to be a crystal in a different way. We're going to have to tile it by 4 G-gons. So just, if we want genus 2, we're going to have to tile our space, our film by regular octagons. Of course, you can't do that. Well, you can't tile a Euclidean film in that way. Of course, we can do this if we change our notion of distance in our 2D space. It's a standard, very, very old trick in mathematics, but it's pretty novel from the point of view of condensed matter, I suppose. The idea, of course, is to work in a hyperbolic space. So we'll replace the original Euclidean lattice with a hyperbolic one. So here's one with an octagonal tiling, which of course this is a regular tiling, but with respect to the Poincare metric. So we'll tile the hyperbolic plane by 4 G-gons, and we'll choose an appropriate periodic potential again. So now, by the way, our Hamiltonian, so H here is the hyperbolic plane, but the other H, our Hamiltonian now has, we replace the Euclidean Laplacian with the Laplace-Beltrami operator. And then we choose a V, a potential that has that has a symmetry with respect to this tessellation of the plane. And of course, such a tessellation has a non-commutative group of translations. That's its Fuchsian group. And the point is that there exist wave functions. You can show there exist wave functions that are quasi-periodic in momentum again, and the property here, the quasi-periodicity property, looks like this. So here, you still have a phase factor, that's chi, and really, you should think of this as a U1 valued function, and here in the condition we have gamma, and this is an element of the Fuchsian group. So when I apply gamma to position, then I get this this momentum factor, this phase factor in front, which is a U1 valued, an appropriate U1 valued function. So this work that I'm talking about all appears in my joint article with Joseph Macheko. So it's a real nice partnership between mathematics and physics. So Joseph is a theoretical condensed matter physicist, and I'm, as you know, a geometer. So this was a really nice thing that we did together, and this was sort of our starting point. But so now, the position space is going to be a genus G surface. It's going to be the hyperbolic plane modulo this Fuchsian group. And we have to keep track of these U1 valued phase factors now. So, and I should say that this is really a map from gamma to U1. So this is a representation of gamma, a U1 value representation of gamma. And also, of course, gamma is the fundamental group of the quotient. So this is really a representation of the fundamental group of our position space into U1. And of course, the space of such representations will be isomorphic to the Jacobian. Okay, so we still have this relationship, this position momentum relationship, that is taking a curve to its Jacobian, but now this is all in Higher-Genus. And this means, of course, that the Brion zone now is over R at least, is a 2G dimensional torus. And so now there's a difference in the dimensions between the position space and the momentum space. In the Euclidean theory, which was really an elliptic curve theory, you had this non-canonical isomorphism between the elliptic curve and its Jacobian, but now it's different. Of course, you can relate the Jacobian geometrically to the genus G curve. It's a birational it's birationally equivalent to the G-fold symmetric product of the curve. But the position really is on one copy of your genus G surface, and momentum is this torus. And so you have this disparity of dimension. So you have something of lower dimension, but a more, let's say, complicated negatively curved geometry for your position space. And then you have something which ultimately is Euclidean, the Jacobian, but is of higher dimension. And so that's the trade-off there in that duality. So now our picture, our story looks like this. So position is this genus G surface, and then this 2G, say G dimensional over C torus is our Brion zone. And an energy band structure still exists over the new phase space. You can again solve Schrodinger, plot your energy surface, and look at its ramification. And the high dimensional nature of the momentum means that richer energy surface geometries and new band structure degeneracies are possible. So one thing we're particularly interested in is if I have some number of sheets coming together. So if I have some branching order, how is that degeneracy resolved as you move away from a high symmetry point? For instance, the origin in the Jacobian is a high symmetry point. As you move away from that, you want to study how the sheets are coming apart. And of course, that there are richer phenomena possible in this higher dimensional picture than in essentially the curve picture we had earlier. And all this is sort of illustrated, and that of course means sort of richer conductivity and insulating properties, at least theoretically possible. And we illustrate this numerically for the Boltzmann surface. So it's a highly regular genus 2 surface with the largest possible automorphism group. So we illustrate all this numerically for a particular lattice that gives rise to this particular Riemann surface as the position space, and with a particular symmetric potential, which was really a kind of generalized Eisenstein series. And this is where the number theory is coming up. We're really talking about wave functions that have an automorphic property here. And the potentials are necessarily sort of generalized Eisenstein or theta series. And again, this is all discussed in this archive preprint from last year, which was recently accepted, I should say. And now I just want to end with some advertisements of what people what are the next steps and what people can do in these areas. And I really want to emphasize the interdisciplinarity of all of this. So really what we have here is a sort of proposal and model for a kind of hyperbolic matter, of which the known topological materials are really just the tip of an iceberg. But this is really an interdisciplinary problem involving math, physics, ultimately material science, and computer science to quite an extent. So the first question you can ask is really, to what extent is there a Bloch theorem for hyperbolic lattices? No, we did not say that, back here, I didn't say that, all wave functions can be written in a basis of such wave functions, just that there exist ones with these quasi-periodic properties. So you can ask, to what extent is there a Bloch theorem that characterizes all solutions to this automorphic, this automorphic Bloch condition? And very soon, Josephine will be posting an article that sort of answers to what extent this is true. And the story involves considering higher dimensional representations of gamma as well, which brings in some nice further algebraic geometry, actually, to do with moduli spaces of stable bundles on curves.
Just to say, so you've got 5 minutes. I think you're nearly done, right?
Oh yeah, this is essentially the last slide. This is the last slide with text on it, at least. But yeah, thanks for the reminder. And then another question you asked is there a hyperbolic crystallography? Can you sort of again, this is really about classifying these materials, and it really comes down to classifying the different kinds of lattices that are possible. And we have a paper out on that. It's a sort of larger group involving a lot of people from the physics side, which is sort of very interesting. And here's the reference. And then thinking physically, what kinds of hyperbolic lattices and circuits can really be actually engineered, and can they be grown as films or printed? Do they occur naturally? And I'm just going to go forward a slide for a second. So actually, there's a paper before us and it appeared in Nature in 2019 by Alicia Collar, who was at Princeton at the time and Maryland now, and collaborators, where they had actually engineered artificial hyperbolic matter. So this is, I think, a septagonal tiling. So this also is genus 2 effectively. But this is a sort of artificial circuit where it's physically Euclidean, of course, but the hyperbolicity is simulated by the tunings. As you go out on these rings, the tunings between these are sort of coplanar waveguides. It's actually a photonic rather than electronic circuit. But the tunings in these waveguides are being modulated as you go away from the center in such a way that mimics the Poincare metric. And actually, they wrote in this paper that what's missing here is a hyperbolic band theory, which is exactly what our work provides. So this is sort of very exciting. But this is, in a sense, completely artificial. Amazing feat of engineering, but one wants to know if these things occur in some natural way. And the last question here is, can they be discovered by machine learning? This has been done to some extent for topological materials, but can you discover the Hamiltonians, the symmetries of these materials through machine learning algorithms, which I think is really, really exciting. And I know there are folks in the audience who are experts on doing this sort of thing, and we should talk about that at some point in the future. But that's really it, and I've been giving talks in the last year and a half now, not only for math audiences, which I'm used to, but also for physics audiences. And one thing that I think physics talks do really nicely is having pictures of people, pictures of collaborators, puts a human side to things. So it's something I've learned to do now as a result. And so these are just my collaborators. So Joseph is sort of second from the right here. With this larger group, we wrote the sort of crystallography paper together. And I just wanted to highlight a couple of my graduate students who are working in these areas. So Sheldon is a beginning PhD student. Christopher is towards the end of his PhD. Be on the postdoc market soon. Have to put in a good plug for him, as one should always do. He's an excellent student. But yeah, it's been a lot of fun working with all of these individuals, and there are more people coming in as well. I'll just say that I'm working with a very talented student named Elliot Kienzl at University of Maryland at the moment, who's also contributing or starting to contribute to this story. And that's really everything. So thanks for listening.
So thanks very much for this lovely talk. Do we have any questions?
I have a question, James. Hi, Stephen. This is George Minich.
Hi.
This is a wonderful talk. I enjoyed it. Have you thought about quasi-crystals? Because you see, that's an aperiodic tiling, right? Definitely people can manufacture those. There's non-trivial nice mathematics that is maybe of this kind of hyperbolic type in some sense, but not exactly like maybe what you're saying. But definitely, that there is some interesting mathematics there. And then, have you thought at all with your collaborators about something like that, about topological matter or quantum matter in those cases? You have an interesting band theory in that case as well, I think, etc.
Yeah, no, so nice to meet you, Jordan, and thanks for this really super question. And I'll say that, yes, we've thought about it, but we haven't, if that makes any sense. It's certainly on our radar. Certainly, we sort of recognize that aperiodic media, aperiodic tilings are probably a good place to start with, looking for actual hyperbolic materials, just as you suggest. And the band theory there is also very interesting to us. And one of the things we want to do is compare some of the numerical band theory results that we obtained, for instance, for this Boltzmann case, with some known examples from sort of the aperiodic setting. But we haven't taken it very far, is what I mean. But this is definitely the right thing to do, the right thing to look at, and it's a really excellent suggestion. And so I think that that's something that we'll be doing in the very near future.
All right, wonderful. Thank you. Thank you for
No
wonderful
problem.
talk. Yeah.
Any other questions for Steve?
Just a comment. Thank you very much, Steve, for this wonderful overview. As I always say, you know more mathematics and more physics than I do, which is awesome.
Oh, I don't think that's true, but thanks.
I never appreciated just studying Brillouin zones as an undergraduate, that there should be modular properties to these things, because you're essentially solving, right, the wave functions of the Schrödinger's equation on this lattice should exhibit some kind of automorphy because of the underlying SL to Z. So if I understand you correctly, so you're saying if you do your bigger story, you're going to get these wave functions explicitly as holomorphic functions, which are Fuchsian automorphic forms. Is that right?
Yeah, exactly. So that you can. What we're saying is that a general solution in this setting can be decomposed essentially into these simpler wave functions coming from these twisted periodic boundary conditions with these phase factors, which are really multiplier systems, unitary automorphic forms.
That's interesting. And these things usually have like integer coefficient expansions in their Q series. Do these things count relevant topologies?
I mean, that's an amazing question. That's something that I thought about, looking at the Q series expansion and trying to find the combinatorial meaning in terms of this particular problem. But I admit I haven't done that yet.
Interesting stuff.
Yeah, but that's very natural and exactly the right thing to be
Let's work
thinking
together. I'm gonna just get an excuse for me to visit Canada in person again.
Oh, you're always welcome. Yeah, and we should definitely be talking about this, and also the machine learning aspect.
Sure.
Of this
Yeah,
too.
I think you mentioned to me last time when I was there. Awesome. Thank you so much.
Yeah, no problem.
Awesome. Any more? Okay, well, it sounds like there's going to be conversations following up, so we'll thank Steve again.